Y'all go ahead and try and work those two problems right there. We'll start class in just a few minutes. See if you can figure them out. Oh, you know what? Hold on that first one. Sorry, I messed up. I wanted it to go to infinity.
So say it just goes to 0/2.
Yeah,
Zero,
yeah.
so.
Go to infinity on that. Sorry.
Okay, that's better.
Just about 2 more minutes. We'll talk about these. All right, everyone. I think that's about right. Hope you all had a good weekend. I know some of you reached out for the quiz. That was due. Well, it's already due, 1 o'clock. So hopefully you submitted that. I'll take a look and see how the class did. And number 4 is going to be kind of like a bonus problem. So we'll see how it goes. If you didn't get it, don't worry about it. It won't hurt your grade. If you got it, then it'll help your grade. It'll be a bonus. All right, so for these limits, I thought we would start off to, recall that we had talked about L'Hopital's rule, right, last time. And let's look at this first one. So let's see what's happening on this first one. X is going to infinity. So we'll always just kind of see what happens first. We have x squared, that's going to head to infinity. Plus, now this one's, I gave you this problem because there's some interesting things happening here. Where does sine go when x goes to infinity?
Positive.
Sine just goes like that, right? That's all it does, just back and forth, back and forth. So even though it's not going to a specific number, right? It's not going to a specific number. Would you agree with the idea that this is bounded? In other words, it's whatever that value is, it's got to be between -1 and 1. Whatever it is, it's between here. That's an important concept because what's happening here is that this is getting bigger and bigger and bigger, and we're adding it to a number that's always between -1 and 1. So if we take a number between -1 and 1, no matter what it is, and we add an infinitely large number, shouldn't that still just become infinitely large? That makes sense? So all of that together is headed to infinity. Now on the denominator, e to the x, well, that's headed to infinity, and that just is from what we talked about last few classes. E to the x looks like this. And so as you go out to infinity to the right, the graph goes up and approaches infinity. So we know that that's headed to infinity. Plus 1 is still infinite. So this whole bottom is headed to infinity. So we have infinity divided by infinity, right? And that's when we can use L'Hopital's rule. We can apply L'Hopital's rule anytime we have infinity over infinity. So I'm going to go ahead and do that. I'm going to take this, say it's equal to L'Hopital's rule, the limit as x goes to infinity. And then what does L'Hopital's rule say you do?
You take the derivative of both the numerator and the denominator.
Yep, separately, right? You just treat them as their own things. So the derivative of the top, okay, derivative of x squared is 2x, plus derivative of sine of x is cosine of x, all over. Now, what is the derivative of e to the x?
E to the x.
E to the x, and then the derivative of 1 is 0. So it's just going to be e to the x on the bottom. Now, if we do the same thing and we run the limit again, we're going to see that, again, 2 times x, that goes to infinity. Cosine of x is bounded, right? Because cosine is between -1 and 1 again. We're adding those together, so all of that together should still become infinite. And then, of course, the bottom is infinite also, right? So we do L'Hopital again, right? We say, all right, let's do it again, because we have infinity over infinity. So we take derivative of the top. This time derivative of the top is just 2 minus sine x over derivative of e to the x on the bottom is itself again. So it's looking like we're getting stuck in this like infinite cycle, but that's not what's happening. So watch what happens on this one here. This 2 is just fixed, right? That's just a fixed number. And then you're subtracting from it this, which is bounded. Okay, right? Signs between -1 and 1. So let me ask you, if I were to take a fixed number and subtract a bounded number from it, shouldn't that be bounded?
Would it be
Think about that.
bounded? Would it be bounded
If
like
I-
as in 3 or 1, between 3 to 1, because it'd be either
Yeah, I
minus
mean-
1 or plus 1?
Yeah, this is at the extremes, right? At the extremes, this would be 2 minus 1 or 2 minus -1, because signs between -1 and 1. Those would be the 2 extremes, right? Do y'all see that? Either way you do it, or any number in between, this whole numerator is bounded. Now that's an important concept. It's stuck between 2 things, no matter what happens. No matter what x goes in there, the numerator is bounded. Now, what about the denominator? Where's it headed?
Infinity.
Infinity. Okay. Now, you cannot use L'Hopital's rule anymore because you don't have infinity over infinity or 0 over 0. What you have is this form of something bounded over something that's becoming infinite. And what will happen in that case? What do you think?
Or does go to 0, because it's going to be, as it gets bigger and bigger and bigger, the smaller it'll just go to 0.
Yeah, think about this. If this is bound, just think about this idea of bounded. This is really important. If this is bounded, let's say it's bounded between 2 numbers. Okay, I don't care what 2 numbers. Let's just call this one A and this one B. So it can be A or B or anything in between. If it's A, that's a fixed number over something that's getting infinite, that's going to get smaller, right? That ratio gets smaller. Even if it's B divided by something that gets infinitely big, that should get smaller. So anytime you have this bounded over infinity, you're always going to have that go to 0. Now, I actually included this in the limit summary. You know how I gave you all that sheet? Let me go back to it. This might make a little more sense now. Do you see this right here in this bottom box? I say fixed, positive or negative over infinity equals 0. If you're taking a limit and you get a fixed number on top, the bottom is infinity, you get 0. Look what I say down here. Here, fixed means non-zero and or bounded. Okay, so when I say fixed here, I mean, yes, it could be just a number like 10 over something that's becoming infinite, or 5 over something infinite. Or if it's bounded over something infinite, then it goes to 0. That makes sense?
Well, it's bounded. You can just think of it as like an interval that functions as a constant almost, and there's a constant over infinity is going to go to 0.
Exactly. Now, what's really cool is to look at the graph of this. Watch. So I'm going to just, this is a different sort of problem, but I'm going to take a bounded function sine of x, and I'm going to divide it by a function that's going to infinity, e to the x. All right. And let's look at what happens to this function as we go to infinity. Can y'all see that as we go out to the right, first it's up and then it's going to come down, and then can you all see there's a little bit of space? It's below the x-axis. Then it comes back. It looks like it might touch somewhere here. And then it's hard to see it, but it's actually a little bit above also right here. Let's move over. I have to zoom out first. Then it's going to go, whoa. Out here somewhere, it's gonna go back below. Somewhere.
Is it negative in that one spot because that's where sine goes into like a -1
Yeah.
value first? Okay.
Yeah, I'm not gonna be able to find it. Let me do this. Let me amplify the sine function.
I was gonna say, if you throw a scalar on there, you might get more oscillations,
Yeah.
make it easier to see.
Yeah, well, it's easier to see here, but eventually E just gets too big. It's above there, and then later on it'll be below. Come on, be below, be below. Yeah, it's
Oh.
below over here. See that?
Mhm.
So this is actually a very useful type of scenario. Let me do something. E to the X, it's too strong. E to the X is getting infinite, but too fast. So let me just put like X here instead. And let me take the scale off of this. Okay, here we go. That's a little bit easier to see. Look, the top is bounded and the bottom is going to infinity, right? As you go to the right. So do you see it's like a sine curve that as you move to the right, what's happening is the amplitude is shrinking. Okay. And so it's almost acting like, this is really cool if you do it this way. If I graph just 1 over X here, and I graph -1 over X like that. So let me make these dotted.
So then cosine of X over X would be basically just the same thing, but just flipped for the sine X almost.
Yeah, pretty much. Yeah. Done. Come on, turn this on. Go here. This dashed. Okay, done. So, all right. So what I did is I took the 1 over X here. That's sine of X is really on top of X. So it's really like a 1 over X on the bottom there. Notice that this sine curve, this one here is always stuck between these two. So I look at it almost like a funnel. It's forcing that function in between the two as you go out here to the right.
Oh, and you just put the restrictions, 1 over X and -1 over X is just, that's the extremes it can be. Okay.
That's right, exactly. And do you see what I've done is I've shown that that red sine function is headed to 0. It actually does, it goes through 0 multiple times. But the thing is, as you go further out, it just gets like more and more narrow, I guess, vertically. The vertical, it gets shrunk down. So it's headed to 0. That's a weird concept because we're saying the limit is 0, even though it actually achieves 0 like infinitely many times. It's just like oscillating, but less oscillation. Now, where would you see this in the real world? Well, think about if you just take like a basketball and you drop it, right? If you just drop a basketball, what happens? It bounces, comes back up. It doesn't come up to the same height that you dropped it from, right? You lose some of the energy, right? When it hits the ground, you lose energy. It can't possibly come to the same height. Then it bounces again, doesn't come up as high, bounces again, doesn't come up as high, and it keeps doing that. And eventually what? It's just at rest on the ground. That's kind of what's happening here. If you're looking at the x-axis like time, right? And let me do something even better. I'm going to put absolute value of this. And that way it can't go negative. Then you can see it more like a bounce. So let's just say the x-axis is time. You drop a ball from, let's say, 1 meter. It bounces, hits the ground, comes back up not as high, bounces again, not as high again, bounces again, then eventually, right? Now, theoretically, it never stops bouncing, but you know, you could argue that when a ball's at rest on the ground that it is actually bouncing because the atoms are actually moving around, but we won't, and we're not going to get crazy like that. So these are called dampened oscillations, right? If I just do sine x, or let me see, just the absolute value of sine x, that is a ball. That's an example of a ball that you're dropping, right? Boom, boom, boom. And it's never losing energy. That's not realistic, okay? So what we need is a function that will actually act more like what we'd see in the real world. So you dampen the oscillation using something like divide by x. We could divide by, how about if we divide by natural log of x, because natural log of x grows kind of slow. Let me take this one out of here. Take that out. Look at that one. That's a pretty good one, right? Now just ignore what's happening here. Just look at this dampened oscillation. It's just getting smaller and smaller and smaller and smaller, right? That's a little easier to see, I think. Okay, all right. So that was the first one. Now the second one, we have something that's going to infinity, right? Times, okay, sine of 1 over x. So first you have to figure out what's happening to 1 over x when x goes to infinity. But that's fixed over infinity, right? Fixed over infinity heads to 0. So this thing is headed to 0. And what is sine of 0?
0.
0. Okay, so that thing is headed to 0. And remember, we're not saying that it's ever equal to 0, right? We're not saying that. We're saying that it's headed to 0. So sine of 1 over x is headed to 0. The x squared is headed to infinity. And that means we have this form of infinity times 0. And that is one of our indeterminate forms. That's something that we cannot tell. And you can tell on our limit summary, we covered this last class, what happens when you have 0 times infinity, right? We know we can use L'Hopital. We got 0 over 0 or infinity over infinity, L'Hopital's in play. But if we get 0 times infinity, we don't have L'Hopital. But I told you last class, you can always do something to make it where you can use L'Hopital. So what is the trick that we use whenever we have this?
Is it the natural log thing?
No, I think no, I don't think the natural log is going to help here.
I turned the 1 over x into x to the negative first, and then I did a product rule. So
You turn it into the denominator?
You pick one of the two pieces, right? One of these is going to infinity. The other one is headed to 0, right? So you've got one of those. You have two things to choose from. You pick one and you drop it to the denominator. The one you pick is totally up to you, but I think in this case, it's easier to see. I'm sorry, I think it's easy to see that leaving the sine x on top, sine of 1 over x on top, and taking x squared and rewriting it as 1 over x squared on the bottom is probably the easiest, because this down here, I should be able to take the derivative of easily. So I'm just rewriting x squared on top as a 1 over x squared on the bottom. Is everyone clear as to why I can do that? I mean, it's just algebra there. Reciprocal, that x squared would actually go here. So we're just making it look different, that's all. But by doing this, if we take the limit, that goes to 0, right? We already know that sine of 1 over x goes to 0. We did that already. But now when we look at the whole denominator, right? The whole denominator, we have fixed over infinity, and that heads to 0. And now we have 0 divided by 0. So what I'm telling you is anytime you have infinity times 0, anytime, you can always pick one, drop it, and then you will always get either 0 over 0 or infinity over infinity, and you can use L'Hopital all the time. So I'm ready for L'Hopital now. So I have to take derivative of sine of 1 over x. So that's composition, and that means I have to use the chain rule. So limit x goes to infinity. Okay, derivative of sine of something is cosine of it. Okay, times. Now, the derivative of 1 over x. Just remember, 1 over x is really x to the negative 1, right? That's what it really is. So to take the derivative of this, I would get negative 1 x to the negative 2. That's just power rule. Bring the power out, subtract 1. But that's really just negative 1 over x squared. And to be completely honest with you, as a Cal 1 student going into Cal 2 at some point, you want to be able to just look at this, 1 over x, realize it's x to the negative 1, realize the derivative of that is negative x to the negative 2, and just write the answer down, negative 1 over x squared. You want to get to that point where you can just do that and not have to write all that stuff on the side. You may not be there yet, but that is a goal. That is a goal you want to get to. What about the derivative of the bottom? We can use that same idea. That's really x to the -2, right? So what would the derivative of x to the -2 be?
-2 over x cubed.
-2 over x cubed. That's it, right there. So it's -2 x to the -3, but then I can just drop the x to the -3 down. Okay, that looks more complicated than what we started with. Would you agree? That looks worse than what we started with. However, we've got something happening here. Watch. If I take this fraction and move it up and do the reciprocal like this, right? Instead of dividing by this fraction and multiply by its reciprocal, I think we get some good things to happen there. Let's see. Sorry, I'm not doing L'Hopital. I'm just rewriting it. Okay, I still have a cosine of 1 over x times, let's see here. The -1 and -2, that gives me a positive 1/2. And then x cubed over x squared, 2 of the x's cancel, I'm left with an x. And now let me run the limit again, and let me see what happens. So let x go to infinity. This will go where? I need to bring my roster up so I can start calling on people.
It's gonna be bounded again, so it's gonna be between. Or no, actually, it'll go to 0 because as it goes to infinity, it's gonna approach 0, right?
1 over infinity will go to 0, right?
And then cosine of 0 is 1, so it's 1
Cosine of 0 is
times.
1. So this is headed to 1. That's not a problem, right? 1 is 1. That's a good thing. And then where's this one headed? So times 1/2 times, and that's headed to where?
Infinity.
Infinity. Okay. We no longer have an indeterminate form. Look, these are headed to numbers, right? This is a number, 1. Here's a number, 1/2. And then we're multiplying it times a number that's getting huge. So what should this thing do?
Go to infinity.
Go to infinity, right? So this is going to go to infinity. You only have a problem when you have 0 over 0 or infinity over infinity or 0 times infinity. Those are problems. Infinity times a number, that's infinity.
0 over infinity, is that bad? Or, well, that's just 0, but
Okay, so yeah, we haven't discussed that. But yeah, we'll do it right now. What would happen if you're taking a limit? Okay, so you're taking a limit, blah, blah, blah. Who cares what it is here? Who cares what it is? And then you do the limit, and this is headed to 0, and that's headed to infinity. What do you think? Do y'all think that's a problem or no?
I would say no, because 0 divided by anything is just 0. So it's like, it's
But
almost.
it's not 0 though. Remember, it's headed to 0.
Oh yeah, that's true, so.
You have
I
to
mean,
remember that.
I guess it would be a problem then.
Let me do it this way. Watch. Could I rewrite this way? 0 times 1 over infinity. Isn't that the same thing? Right? Okay, so you got one thing that's headed to 0 times one thing that's headed to
0.
0. Okay, and what's 0 times 0?
0.
0. So the way I look at it is this. The numerator's sitting there going, oh, I want to be small, right? I want to get really, really, really small. And the denominator is like, well, hey, guess what? I'm going to divide you into smaller pieces. So I'm going to make you smaller even faster. So they kind of help each other out and you get to 0. The issue is when you have 0 over 0, then you have an issue, or infinity over infinity, because you can't tell who wins the battle. Here they're helping each other. They're like assisting each other. We're going to talk more about that in a minute. I wanted to take that problem x squared sine of 1 over x. Let's graph it. I just want to see it. We said the answer is infinity, right? So if I take x squared and I multiply that times sine of 1 over x, when we look to the right, this graph should take off. Pretty crazy looking graph. Goes like this, right? It's trying to act like a sine function in the beginning. And then it starts to oscillate and get big. And then let's see, this thing eventually just takes off. I wondered, man, it almost looks like a line at some point, doesn't it?
Yeah, you go far enough out and you can't even see the
Yeah.
oscillations.
So do you see, everyone, do y'all see that as we go to the right, this thing grows, right? It goes to infinity. We were able to discover that by doing our L'Hopital's rule. Okay. We move on. Still in L'Hopital's rule. So if we look back at our limit summary, we should now, well, there's a lot of stuff we know how to do on here. I've already been through this with you. We know how to do that. We know how to do that. We know how to do that. We now know that if we see this, we have L'Hopital. And we now know that when we see this, we can drop one, right? We drop one of them. And then we do L'Hopital. And now what we want to do is see if we can't handle a couple that we have not seen before. We have not seen 1 to the infinity, 0 to the 0, and infinity to the 0. We have not seen those. Those are 3 new forms that we've stayed away from on purpose. All right. So,
Question.
yes.
What, the infinity to the 0, isn't that always going to be 1 though? Because the whole rule is anything to a 0 power is just 1.
So Cody is asking a great question. Isn't anything to the 0 1? Y'all agree with that? If I give you a number and tell you to raise it to the 0, the answer should be 1. I agree with that, except 0 to the 0, Cody. 0
guess-
to the 0 is undefined.
And 0 falls within infinity, so that's why it doesn't work.
No,
No?
because the reason why infinity to the 0, we're talking about it, and it's not 1, is again, this is the thing that we're looking at here is a limit summary. These are limits we're talking about.
Approaching infinity.
Okay, approaching 0, never 0, approaching 0. Here, what we're saying, and let me write those down on our notes. We're saying 1 to the infinity, 0 to the 0, and infinity to the 0 are all what we refer to as indeterminate forms. Meaning if I take a limit and I get one of these 3 things, we don't know the answer. Let me give you 3 examples under each one of these to give you examples of each of these, okay? So let's say that we take a limit. Let's go x goes to 0, and let me do cosine of x raised to the 1 over x. And let's approach 0 from the right side. Okay, let's look at this one. As x goes to 0, what's cosine of 0?
1.
1. So it's approaching 1, isn't it? The base is approaching 1.
Mhm.
We're not saying it is 1, it's getting closer and closer to 1. So maybe it's like 0.99999999742, right? And then he gets a little closer, 0.999999999999421, something, right? It's approaching. So this is approaching 1. And what about 1 over 0? Well, that's a fixed over something that's getting smaller. What will happen? Fixed
It's
over
gonna go to
something
0.
smaller should get bigger,
Or bigger. Oh, yeah.
right? It should get bigger. So I'm not saying, remember, we can't plug 0 in here because that's undefined. It's a limit. What's happening? If I take a number to the right of 0, come in from the right, take a number really close, 0.0000000000000000000000001, okay? Take that number and plug it in right there. 1 divided by that number is going to be a huge number. Make sense? So what we have here is exactly the form the base wants to approach 1 and the exponent wants to approach infinity. Approach 1, approach infinity. Do you see that? This is limits. This is not like numbers. If I just sit here and say, hey, everyone, what's 4 to the 0? Everyone should tell me 1, okay? But we're not talking about limits. There, we're just talking about evaluating a numerical value. That's it. 4 to the 0 is 1. Done, move on. Okay, let's look at the next type. How about this one? This one will be interesting. How about the limit as x goes to 0 of x raised to the x? And let's approach from the right just to keep things consistent here. So imagine you take a number that's really, 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 really small and raise it to a really, really, really small number.
You're gonna approach 0.
Will you?
Or wait, no, wait, hold on.
Try it on your calculator. Take 0.00001 and raise it to the 0.00001 and see what you get.
It's reaching 1. It's trying to get to 1.
Trying to get to 1. Does it look like it's getting close to 1?
0.9999986.
0.99999.
Very close.
Yeah.
So it's not approaching 0, is it?
No, it's approaching 1.
Okay, that's for that particular problem. Okay, that's
Right.
for that particular problem. Now, if we change the problem a little bit, we can make it do something different. The whole idea that I want you to understand, though, is this. The base is approaching 0, right? So the base is like, hey, I want to be 0. Please let me be 0, please. And then the exponent's like, well, wait a minute, hold on. I like to take things, and when I raise things to 0, I like to turn them into 1s. And the base is like, wait, but I want to be 0. And the exponent's like, no, but I want you to be 1. And it's this battle. We don't know who wins. The 0 up here does not always win. Okay, it does not always win. It depends on the problem. So this is an indeterminate form. This right here is the same sort of battle. The base is sitting there saying, hey, look, I want to be infinitely big, right? But then the exponent's like, well, wait a minute, I like to turn things into 1. So they battle each other. I'll show you a limit, an example of that one. Limit, let's just let x go to infinity. And let's do x raised to the 1 over x. So if x goes to infinity, the base becomes infinite. And then the 1 over infinity goes to 0. And that right there is infinity raised to the 0. And that's indeterminate. So Cody, again, and everybody, this is in a limit, right? When we're talking about a limit, we have to go figure out what's going on.
Right, okay.
All of these should be questions. So remember how we used to get 0 over 0 and we say, oh, that's bad and we need to do something?
Mm-hmm.
That's what we're saying with these. 1 to the infinity, 0 to the 0, infinity to 0. Those are all bad and we need to do something. Now, there are certain other cases that are not bad. Okay, let me show you an example. I don't want you to confuse all of these, you know, that like any scenario you ever get. Like, what if you had infinity to the infinity? So the base is like, hey, I want to be big. And the exponent's like, well, guess what? I'm going to multiply you times yourself over and over and over and over. I'm going to help you get big, right? There's no conflict here. This would just go to infinity. What if you had 1 to the 0? So the base is like, hey, I want to be 1. And then the exponent's like, well, guess what? I like to
want you to
turn
be
things
1.
into 1. And so they don't fight each other. It just becomes 1, right? What else could we have? I'm trying to think of another example. Oh, how about this one? 0 to the infinity. That's a good one. So the base is like, hey, I want to be really, really small, right? And the exponent's like, well, I'm going to multiply you times yourself over and over and over. What happens to a small number when you multiply it times itself? Does it get bigger or smaller?
Smaller.
Smaller,
It's
yeah.
smaller, right? You have to be careful. Most people think that when you multiply a number times itself over and over, it gets bigger. Not always the case, right? If I take 2 and I keep multiplying 2 together, that's going to go to infinity, right? But if I take 1/2 times 1/2 times 1/2, and I do that forever, each time you're halving it, right? So These two multiplied is a fourth, and then go again, it's an eighth, then a 16th. It gets smaller and smaller and smaller. So when the base here is saying I want to be small, and the exponent's like, well, hell, I'm going to keep on multiplying you together, that they're going to work together to make it small. So that's going to head to 0. Does that make sense, everyone? You have to be a little careful with these. It's not just any arbitrary combination of ones and zeros and infinities. These three are the ones we can't figure out.
I have a question. So what if
Yes.
it's like 2 to the infinity? Would that apply or no? Like, no,
2
you
to
have
the
1 to the
infinity
infinity.
would not be an indeterminate form.
Okay.
Because if you had a limit, let me just do this. How about this? Limit x goes to infinity. I'll make this somewhat cool. 2 cosine of 1 over x to the x. How about that? So look at what happens here. If x goes to infinity, what's 1 over infinity go to?
0,
Okay, what's cosine of 0?
1,
Okay, what's 2 times 1?
2.
2. So this base is headed to 2. Everyone agree?
Mhm.
Okay, and where's the exponent headed to?
Infinity.
Infinity. So we get something that looks like 2 to the infinity, which is what Christian was just asking, right? That's not indeterminate. 2, the base wants to be 2, and the exponent's like, well, I'm going to keep on multiplying you together. 2 times 2 times 2 times 2 times 2 forever. That's going to become infinitely large. One to the infinity is a problem though, right? 1 to the infinity is a problem because if you have a number that wants to become 1, right, instead of 2, if it wants to be 1, then 1 times itself over and over and over, right, should be 1. 1 times 1 times. But remember, it's not 1. We're not saying this is 1. We're saying it's close to 1. So if you take 1.000000001 and then start multiplying that over and over, who wins, right? Does it get closer to 1 or does it get bigger? So it's a battle we have to figure out. I hope that that illustrates kind of like the trouble that we have to be able to deal with. And now it's a matter of, can we do these? Okay, so I'm going to do each one of these one at a time. Let's do this first one. Well, you know what? I'll copy them all over here on new page. Oh crap, I'm in the wrong. No, there we go. Okay, so let's start with this first one. We're going to take the limit as x goes to 0 from the right of cosine of x raised to the 1 over x. And I will reiterate what I said just a moment ago. If we have 0 over 0, we're infinity over infinity, L'Hopital, we're ready to go. If we have 0 times infinity, we're going to drop 1 and then use L'Hopital. These three, all these three here, are all done the same way, okay? Anytime you see one of these three, here's what you're going to do. You ready? We have to first realize it's an indeterminate form. So we would now realize it's 1 to the infinity. This is bad, okay? We have to realize that, which we've already done. So we've got a bad situation. Here's the way we attack them. What you do is you call this limit y. Now this is going to be the first time you've seen this, so it's going to seem strange. We're going to call the limit y. All right? I'm allowed to do that. I can call it y. So everyone, we want to know what y is, right? So just remember, we want to know what y is. Agreed? So check this out. I'm going to bring the natural log in now. So I'm going to take the natural log of the left side. And then when I do the natural log of the right side, I don't have to put the natural log on the outside of the limit. I can actually move the natural log on the inside of the limit. That is a property of limits that allows you to do that, but I'm not going to prove that to you. You just have to take that on faith that when you take the limit, the natural log of a limit, you can do the limit of the natural log. Why do you think I'm doing this?
To the front.
Yep, I want to move this out to the front. Okay, so now here's what we have. Notice I'm writing it left and right hand sides together. Natural log y equals limit x goes to 0 from the right of 1 over x is now in front of the natural log of cosine of x. Okay. Any questions? Let's see what that did for us. Let's run the limit again. As x goes to 0, 1 over 0 heads where?
To, it heads to 0.
Nope.
Oh no, 1 over 0.
1 is fixed, right? The bottom gets smaller. Fixed
Just-
over small number gets
Infinity.
bigger.
Yeah, infinity.
This goes to infinity. Okay. What was cosine of 0?
1.
1. What's natural log of 1?
Isn't that 0 as well?
That's 0. Okay, so this goes to 1, but natural log of 1 heads to 0. So what do we have now?
We have infinity times 0, so we could drop
Any
1.
times 0. So now we can drop 1. You see that? This goes to infinity. This goes to 1. Natural log of 1 goes to 0. And now we have infinity times 0, which is the previous type. So we pick 1 and drop it. So let me show you which one I'm dropping. I'm going to drop the 1 over x. But when I write it on the bottom, it's actually going to look weird. It's going to be natural log of cosine of x over x. Because that's what happens when you move this down, you do the reciprocal of it. So it flips it and becomes just x. And check for yourself if you want right now. We already just said that this piece here goes to 1, and then natural log of 1 is 0. So the top heads to 0, and the bottom is headed to 0. And now we finally have L'Hopital at this point. Okay? Questions? Now watch what I do. Natural log of y equals, by L'Hopital's rule, the limit as x approaches 0 from the right. Now I'm going to take the derivative of the top and bottom separately. Okay, derivative of natural log of something. Let's see. Let's call on people. This will be fun. Alejandro, you there?
Yes, sir.
Okay, so help me out with the derivative of the top.
All right, so it's going to be kind of like a chain rule here. So first, we're going to take the derivative of natural log, which is going to be 1 over x, or I guess in this case, be 1 over cosine x.
Good, 1 over cosine x, okay.
And then you'd multiply that by what's inside, which would be negative sine x.
Perfect. Everyone got that? That's the derivative of natural log of cosine of x. Good, how about the bottom?
That's just going to be 1 since this is
1.
an x.
Yeah, so we don't even need it there, right?
And not really.
Yeah. Okay, good. Do you recognize sine over cosine? You don't need to recognize it, but it might help. You don't need it though. Let's just leave it. Let's just leave it as negative sine of x over cosine of x. Okay, Alejandro, you're doing good, so I'm just going to stick with you here. If we let x go to 0 now, Alejandro, what's sine of 0?
It's going to be just 0.
0. So top's headed to 0. Where's the bottom headed? Cosine of 0.
Cosine of 0 is going to head to 1.
1. Okay, is that a problem? Is 0 divided by a fixed number a problem?
No, that should be just 0 right there.
That's just 0, right? Everyone, that's just 0. Okay, good. So what we're saying now is that the natural log of y has to be 0 because the right-hand side of this limit became 0. We're almost there. Remember, what did we want? We didn't want to know what natural log of y was. We wanted to know what y was. So how do we get rid of a natural log if we want to get y by itself? What kills natural logs?
Oh, e to the x.
E, right? So watch what I do. I'm going to do e to the natural log of y on the left side, and then e raised to the 0 on the right side. So I'm just applying the exponential function to both sides of the equation. On the left side, I just get y. And now finally, this is not a limit, this is a number. E to the 0 is 1.
Then do we set 1 equal to the original and
No,
reverse
that's our
solve?
answer.
Oh, that's our answer. Okay.
Yeah, because remember, we called this limit y, right? We had no idea what the limit was, but we just decided to call it y. So at the
Oh,
end of the
okay.
day, I want to know what y is. And then doing all this work, we were actually able to determine what y is.
And then even if you converted that to tangent, so it'd be like negative tangent of x, it's still tangent of 0 is 0, right? So,
Tangent 0, 0, exactly. So you'd still get 0. Okay, so this is the way this works. You do your limit. If you get one of those 3 weird forms, okay, if you get one of these 3 weird indeterminate forms, then what you're going to do is you're going to call that limit y. Then you're going to take the natural log on both sides of it, which will always allow you to pop this out front. Then I guarantee you at that point, you're going to have something like this. And then you can drop 1, and then you can use L'Hopital. And then at the end, just don't forget, you have to get back to y. Okay. How about y'all try this one on your own? Okay, try that one on your own. I'll give you a few minutes, and I'll zoom out so you can kind of see my work here. I hope that that's okay. I'm asking you to do limit x approaches limit. That's not a limit. Limit x approaches 0 from the right of x to the x. See if you can figure out what that is. And there's my work for the previous one, just to kind of help guide you along. And let's take about, I don't know, 6 minutes. See how it goes. I just launched a poll. You can maybe let me know if you get it or when you get it.
I'm assuming we were supposed to say yes if we were done.
Yeah, when you finish, you can just let me know. Another 30 seconds. All right, let's talk about this. So let's see. Jorge, are you here? We only have like 5 people said they were done, but we'll keep going. Jorge, are you there? Jorge, last call. Oh. I see that you unmuted, but I can't hear you. No go? Okay, how about Bree?
All right.
Did you get it?
Yes.
Okay, so you want to walk me through it? What was the first thing you did?
Okay. The first thing is I took the natural log of both, and I dropped down. I got ln of x to the x, and then I took the power of x and moved it in front of the natural log. So
Okay, so I'm okay with that. Did you call this y first?
yes, yeah.
Okay,
Sorry. I did
okay.
that.
So you start with calling it y, and
Yeah.
then you're doing natural log on both sides of the equation.
Yeah.
Okay. And then you did natural log of x to the x, and then you pulled the x out.
Yes. Yes. Sorry,
Okay.
I'm worse.
No, it's all right. Just got to make sure we're all understanding what's going on. Okay, so you pulled the x out.
Yes.
Now, again, and Bree, this is after us already knowing that this was 0 to the 0, which is bad. Okay, right?
Yes. Mhm.
Okay. So can you tell me, Bree, at this point, what we have? Like when we take a limit, where this is heading, where that's heading?
X is heading to zero,
Yeah.
right?
Mhm.
Yeah. Times infinity.
Negative infinity. So
Negative.
yeah, remember everyone that natural log of x, the graph of that, here's natural log. Right, that's what natural log looks like. So as you head to 0 from the right, it heads down to negative infinity. So we get negative infinity here. And the fact that it's negative doesn't matter. We have 0 times infinity. Who cares about the signs? Now what? How do you
Now-
deal with that?
Now we can drop one, and I chose to drop the X.
Yeah, yeah. So you rewrote the next line would be this, and then what? On top natural log, what's on the bottom?
Yeah, 1 over X.
1 over x. Okay,
And then from there, I did then I could do the L'Hopital's rule.
okay, so here comes L'Hopital.
Yeah. So for the numerator, I got 1 over X.
Okay,
Is it times?
over
Well, 1 over X times 1 would be 1 over
times
X.
1, yeah, okay. With the chain rule, yeah.
Yeah. And the denominator, I got negative X to the negative 2.
Okay, so I'm gonna write that as negative 1 over x squared. Is that okay?
Yeah, I eventually did that on the next step.
Okay.
Okay, so
Does
we'll go.
anybody have any questions up to this point? This is all correct. Derivative of this is this, derivative of that is this. No questions, we proceed. Okay, now what?
Okay, then I multiplied the numerator by the reciprocal of the denominator. So x squared over 1.
-1.
Yeah, -1.
Mhm.
And then I got x squared over -x. I didn't get
Okay.
that.
Yeah, x squared over -x,
Okay.
which would become just
X, negative x.
negative x. Okay, negative x. There you go. All right, good. Now what?
Then I took E.
Okay, so hold on. Before you do that, now take the limit, right? Let x go to 0.
Yeah, okay.
And you've got 0 on the right-hand side.
Mm-hmm.
So we finally got to what this limit is, right? Because if x goes to 0, then -0 is still 0, and you get 0 here.
Yeah.
So we have natural log of y equals 0, and then you brought in the e
Mm-hmm.
on both sides, and that gave you y is equal to 1, right?
Yes.
Same answer as the last one. I wonder if we always get the answer 1. That's the answer. We're done.
I was thinking about that. I mean, whether you always get 1 or not for these, it's.
I don't know. Let's try the last one. So do you think if we get 1 on this last one, do you think we can say it's always 1?
I don't think so, no. I mean,
Yeah.
I feel like you gotta have more of a data pool.
Yeah, so that's one of these interesting things about math. Let's say that you have 3 examples and every one of them gives you the same answer. Can you deduce from that anytime we have a limit like this, it's going to give you an answer of 1, right? And that's just not the way math works. Something can happen a billion times in a row. It doesn't mean that the next time it's going to happen. So proving things mathematically is hard. Okay, let's do this. We have the form here we have is infinity to the 0. This is bad. Okay, I'm going to try to work quickly through this. I'm going to call this thing y. I'm going to take natural log of y on both sides. When I do natural log, I know that the 1 over x is going to come out front, in front of the natural log of x. So I skipped a step there. I actually just popped the power out to save myself 1 line.
X over x.
Now I'm going to rewrite that as, I'm going to take that 1 over x and drop it to the bottom, leave the natural log on top. So it'll just be natural log of x over x. And now I'm going to apply L'Hopital's rule because I have infinity over infinity. And so I get 1 over x over 1. And what happens if x goes to infinity of 1 over x?
0.
0. So you get 0. And so you do e again. This is the 3rd time we've been through this. And you get 1. Okay, so yeah, you could maybe make an argument, hey, maybe the answer is always 1. You know, maybe. It's not. So let's do another example, okay?
So I felt like if we tried to make the argument, you have an example ready to show we're wrong.
Yeah. So here we go. I like to give the analogy, you know, the sun rose today, right? Like there was sunrise today. I mean, it was cloudy and rainy, but the sun definitely came up today.
Yeah.
Right. And it's been doing that for millions and millions, if not billions of years.
Yes.
Okay. Does that mean it's going to come up tomorrow?
Fair play. No, we could die.
Right.
It could blow up.
Yeah. Who knows? Right. Just because something happens a billion times or a cajillion times in a row, then that's not enough that's mathematically, that's not a proof. I'll show you a real quick example of what I'm trying to say. What if I define a function, okay? And this function is equal to 1 if x equals, let's say if x equals 10, and it's equal to 0 if x is not equal to 10. I'm going off topic here for a second. Okay, so if you were to look at this function and graph it, it's at 10, it's 1. So if I go out to 10, you go up 1 and you put a dot, right? That's the graph of that function. But if you're not 10, it's 0. So everywhere else, it's 0, right? Everywhere else, it's 0. Now I'm going to put a little hole here because it's actually a dot up here. So if you were to sit here and look at this function and just look at its graph, right? Forget this. Just look at the graph. Unless you knew this, right? If you were to be looking over here, all the way that way, or over here, all the way out, for an infinite number of values to the left and an infinite number of values to the right, it's 0. So if you looked at, like, you know, billions of values, billions, trillions of values, you would get 0 each time. That would not be enough for you to say, oh, well, then this function just has to always be 0. No, there's one point where it's not. So in mathematics, just because something happens over and over and over again, that is not enough to prove that it will always be that case. That's why proofs in math are hard. You have to prove something and leave no doubt, okay? All right, let's get to the problem I want us to do.
Almost sounds like anything outside of a law is basically almost a level of probability.
This one right here is a classic example, and I've shown this to you already. But I would like to see if you can do it first, all right? So take your time, okay? Make sure it's a bad situation. Make sure you're getting one of those indeterminate forms. Whatever the form is, do what you need to do. Let me give you, I don't know, 6 minutes. I'm gonna call, just so you know who's coming up. I'm calling on Justin and let's see, Bree, I called on you. Justin, Justin and Brian are the next two on the docket here, okay? 6, 7 minutes, see how far you can get with this. Sorry, Cody, I didn't get that text till now. So
Yeah, I forgot to solve for
it's not zero.
y. Yeah, I forgot to solve for y, I think.
Let's go another, I don't know, 2 minutes. The answer is not 1, and the answer is not 0. All right. Justin or Brian, are either one of you done? No? Brian?
No. I can tell you what I've gotten so far if you'd like, but
Yeah, so what we can do is let you kind of walk me through to the point that you kind of get stuck, and then maybe we'll ask Justin where he is on it. Go ahead. What did you do to start here?
so I was looking at I looked at the start and I saw that it was the 1 plus 1 over x. So that would go to it would ultimately go towards 1, wouldn't it?
Yes.
And then x goes to infinity, so we'd have the 1 over infinity there. And so Then for the next step, I put the natural log on each side.
Okay,
So
you call this thing y.
yeah,
And
so
then
y
you put the natural log.
y equals the limit of x to infinity, x times the natural log of 1 plus 1 over x.
Okay.
And
Justin?
then, oh,
Hold on, no, I was gonna ask Justin, I know he's working there. Did you get the same thing so far, Justin? You got that? Okay,
I have that as well.
okay. And then keep going then, Brian. What did you do?
I put the x on bottom by putting a 1 over x.
Okay, that's right.
And then from there, I used the L'Hopital's rule.
All right, this is
So-
probably where you ran into some issues. That's it.
Well, I put for the top, it's 1 over 1 plus 1 over x for
Yeah,
the
okay. Yeah, so Brian's taking the derivative natural log of something, right? Which is 1 over that something, that's here. So
Mhm.
here's the something inside, 1 over that, that's derivative natural log. Okay, continue.
times negative 1x to the negative 2.
Yeah, -1 x to -2, that's fine. So you took the derivative of the yellow,
Mm-hmm.
derivative of 1 is 0, derivative of 1 over x is -1 x
To
to
the
the
negative.
-2.
Mhm.
Can I write that a different way? Is it all right if? can
Yeah,
I
yeah,
write
it's
negative
fine.
1 over x squared? Okay. Okay, all of that is over what?
The same thing as before, so the negative 1x to the negative 2,
Okay,
because it's the, yeah. So
Which
that
is not
you could
the
write it
same
the same way, yeah.
they're the same.
And yeah,
So they're the same. So what can you do?
I didn't know if you were able to cross them out, so I didn't want to like.
There's multiplication here, so you can't.
Yeah. Okay. Yeah. So did I? Or wait, hold on.
Justin, is that where you were getting a little hung up with this part, or
Uh,
did you have trouble with the derivative part?
Or
I
actually, no, I did cancel those. Never mind.
Yeah.
I moved the -1 over x squared in the numerator. I put it on top of
Did you do like
1
that
plus
or
1
no?
over x. No,
Did you bring it? No.
I've-
Did you put it way up here?
yeah, I'm not sure why I did that.
Yeah, so that if you get the algebra and you start doing something weird, not weird, but you have to see the cancellation here for this to work. If you start doing other things algebraically, you could still get it, but it just might take longer.
Okay,
To see the immediate cancellation is the cleanest thing. If we just go to the next step now, we'll just write what's left. All that's left is 1 over 1 plus 1 over x. Then what do we get here?
Well, see, put it equals 0, but I'm not a.
Well, what does 1 over x head to?
To 0.
0, okay. So 1 plus 0 is
1.
1. 1 over 1 is
1.
1. Okay, that's it. It's headed to 1. So, but not the answer is not 1. Natural log of y equals 1, right?
And so then you'd e
Now
both
you need
sides.
to e, right? Now you need to e. So these cancel and you get y equals what?
E.
E. And remember, e is a number.
Yeah, my problem, I was forgetting to put 1 over x on the bottom. I was just smacking x down there. It was throwing me off.
So here's what we're saying. This is kind of the cool thing, I think. We're saying that e is equal to the limit as x goes to infinity of 1 plus 1 over x raised to the x. That's what we're saying, right? That's the original problem. So if you don't believe this, you just get on your calculator and you can start plugging in numbers for x here and make them get bigger and bigger and bigger. If you plug in like 10, you'll get some answer. Plug in 100, you'll get another answer. And I promise you, the bigger your number gets, the closer and closer it gets to e. Watch, I'm gonna try and do it here. Okay, so what if I do 1 plus 1 over x, oops, raised to the x. There we go. Get rid of that. Zoom in on this. This is the graph of that. As you go to the right, it actually has a horizontal asymptote. So as you go to the right, you get closer and closer to E. Now look, the computer, look at what the computer says. Computer says that E is 2.71828182846, right? That's what it says. Okay, if I go to the red graph, let's go to just 10. If I go to 10 and I ask what's the value, look at the value of that red graph. It's 2.594. It's not very close to E, is it? But as you go further out, let me go to 100. Let's see how close we are at 100. At 100, what's the value of the red one? 2.70. It's closer, right? It's closer. Let me go out to, see if I can go out to 1,000. This is going to be hard. Well, let's go out to 10,000. Is that okay? Now I'm going to have to zoom this forever to get to it. So let me do this. I'm going to take the blue one off so it'll be easy to get the red one. At about 10,000, it's 2.718, right? Which is the first 3 correct decimal places of E. If you want more precision, you go further and further out. Now remember, I told y'all that E is an irrational number, meaning the numbers, it's like 2.718, and then those numbers just keep changing. There's no pattern. Okay. If you wanted to get more of the numbers, you would just use that limit. You would just go out and just plug a bigger and bigger number in. And you get more and more decimal places. That's the way E is defined. So that's what I'm telling you. Like that's a way you, that is actually a correct definition of what the E, what the natural base is. Okay. So I hope that what you've taken from this is that the answer is not always 1, right? And that for all these problems, you're going to have to do y equals natural log both sides, drop the power out, drop 1 to the bottom, L'Hopital, and then at the end E. Okay, that's how you handle all these. I think that's probably good as far as examples. Are y'all okay? Or maybe we should do one more. Let me see if there's one in the book that looks interesting to me at all. What is this? 3 point. Yeah, let me see. All right, y'all want to do one more? Practice one more? Okay, we'll do one more. How about this one? Limit x goes to infinity of e to the x plus x raised to the 1 over x. All right. Is it helpful to let you have time to try and work it a little bit? Yeah. Okay. Okay. Have fun. While y'all are working that, I'm gonna bring up something, so just ignore what's on the screen. Okay, shall we discuss? Let's see. Cruz, you want to go?
Sure.
Did you get it? Were you finished?
No, I got to the last part where it's kind of stuck still.
Okay, so let's go with it. So you call this thing Y because when you do this, what form are you getting?
I'm sorry?
What form of the limit are you getting? Like, what does this head to, and what does that head to?
So that one right there in the parentheses is heading to infinity, no?
Mhm.
And then over here is heading to 0.
0, and that's bad, right?
Yes.
That's bad. So remember, if y'all ever forget, go back to your limit summary, right? Infinity to the 0 is bad, right? Okay, now, so you call Y, you did natural log on both sides, yes?
Yes.
Okay, did you pull the 1 over X out front?
Yes.
And then you have the natural log of e to the x plus x, like that?
Yes.
Okay, good. And then did you drop the 1 over x to the bottom?
Yes.
When you did that, did you just write it as x on the bottom?
Yes.
Okay. All right, I'm with you.
Okay.
Then L'Hopital?
Yes.
Okay, what did you get when you did L'Hopital? Let's see if you got the derivative right.
Okay. Well, what I got with L'Hopital is I got 1 over e to the x plus x
Okay, good.
multiplied by e to the x plus 1.
Yes. All over.
All over 1, which we don't
1.
need anymore.
Yeah, so that doesn't do anything, right? So we could rewrite this as,
I rewrote it as e to the x plus 1 over e to the x plus x.
yep. Good. Now, if x goes to infinity here, Cruz, where does the top head? Where does the bottom head?
Infinity over infinity still, no?
Yeah.
So we got it. Right? Or no?
Yep. L'Hopital again, right?
Yeah.
Let's do it again. Okay, what do you get?
It should just be e to the x on top. And then e to the x plus 1.
Okay. Do you see where we're headed with this? Do you see that we still have infinity over infinity?
Mm-hmm.
Do you see what'll happen if we do L'Hopital one more time?
It'll be 1.
It'll just be infinity over
Yeah. You'll get e to the x over e to the x, right?
Yeah.
Which is 1.
That's pretty cool.
And so we have natural log of y equals 1. And then e to the natural log of y equals e to the 1. So y is e. Wait a minute. We got a totally different, we got e again, didn't we?
Mhm.
So this is another way you could write e. There's an infinite number of representations of e, but this is another one of them. So I think the key to that problem is to see that we could use L'Hopital's rule multiple times. We wanted to use it enough times to get to something that algebraically reduces down to a nice number, right? Cruz, does that all make sense?
Yes.
Okay, good.
I was just gonna say, it kind of felt like we're almost using L'Hopital's rule to do that similar thing when you have like the x squared, you take your bottom denominator and you're trying to clear the x's till you get constant over constant.
Yeah, pretty
Nice.
much.
Yeah, it's kind of the same thing to me, yeah.
It was like, it was getting cleaner each time we did L'Hopital.
Right.
Yeah.
Which is just like with that limit thing, like the x squared something something over x squared something something.
So I wanted to show you, oh, hold on, just real quick. Okay, sorry, my daughter's baking a pizza and I don't want her to burn the house down. Okay. All right, so I wanted to show you now from my Cal 2 class. This is me doing the homework solution videos. So this is almost halfway through the class. I'm doing this problem. Let's see, it's 1 hour, 22 minutes, 21 seconds. I'm not going to go through this whole problem and play it twice as fast. Let's see. Don't worry about what I'm doing right now. All right, I'm working out this thing called a definite integral. To do this definite integral, I'm having to do this thing called integration by parts. Working through. I might need to speed this up. Still working. I'm having to do a limit in here in this problem. It requires a limit. And we're almost there. Okay, here it is. At this point right now, I have to take the limit right there. I'm covering it up. It's the limit as t goes to 0. You can't see it's behind me, but I'm taking the limit as t goes to 0 of this right here. So if t goes to 0, t squared goes to 0, and natural log of 0 goes to what? Negative infinity, right? And so a Cal 2 student would have to know how to deal with that, right? So I'm actually showing it right here. I did the 0, I dropped the t squared down, right? I dropped it, and now I'm rewriting it. I'm taking, well, no, I'm not doing the derivative yet. I'm just showing it's infinity over infinity because I dropped it. And now I can do L'Hopital on top, or L'Hopital derivative top over derivative bottom. And then I'm just going to algebraically clean it up, and I'm going to get an answer here. So the point is that within a much bigger problem, right? Let's see, took me what, almost 4 or 5 minutes to get to this one little piece of this problem that requires this. Okay, so L'Hopital kind of creeps up in different places within the class, so you just have to be prepared for that sort of thing. All right, questions? And then this was an exam. Where is it? Thought I had it up here. Yeah, this is an exam question that I gave my Cal 2 class, where again, they do some stuff. And then right here, at this point right here, I circle it in blue. This is a limit as t goes to infinity of natural log of t over 2t squared. And that right there goes to infinity over infinity. And so I'm doing what we're doing right now. I just do it real quick over here and get 0. So just trying to show you it shows up, okay? All right, I think we've exhausted everything here. Now it's just a matter of you doing the homework and making sure you can handle it. So as far as the schedule is concerned, you're now clear to do the rest of these limit problems. This is the same homework assignment. So everything from L'Hopital's rule, enjoy. Okay, with that said, do y'all want to do a break? We can do a short break. It's 2:40, it's a good time to do it. Why don't we do a 10-minute break? I'll put a timer up here, we'll come back. We'll make sure my daughter's okay. All right, we'll meet in 10 minutes. Okay. Ready? Here we go. Chapter 4. Moving into a new chapter. So we're going to be doing applications of differentiation. So it's time to see what we can use differentiation for. We've already seen related rates. We've seen how you can go back and do limits now that we know more about derivatives. But now we're going to get into like the real valuable, important information about applying the differentiation. In the first section we're going to cover, and all we're going to cover today, is this idea of maximum and minimum values. So let me give you kind of just a broad idea of what we're going to be doing here in chapter 4. Basically what we're doing is there's two different sorts of points of view that we have. All right. The first thing we're going to do is we're going to try and find what we call the maximum and minimum values for a function where our function starts and stops somewhere. So maybe it starts here at A, ends here at B, does some weird things. And we want to find the highest and lowest points on that graph. So we want to find, like, where does it reach its highest point and where does it reach its lowest point? Okay. That is what's referred to as the closed interval method. That's what 4.1 is about. Okay, so we're going to take a function, define it on some interval, and then try and find its highest and lowest points. That's actually going to turn out to be not that hard to do. After we do that, we're going to find what's called the local max and minimum values for a function, but this time we are not going to restrict the function to a closed interval. This time the function can be doing all sorts of crazy things. But these arrows at the end mean that it just keeps going forever. So what we're going to be looking for on those problems is, where do all these peaks and valleys occur? And I told you all this in the beginning of class, like, one of the ultimate goals for us is to be able to take some arbitrary function and find its highest and lowest points. The first method is how we do it if it's a function on a closed interval. The second method, this is how we deal with functions on an open interval. You understand the difference between closed and open? What I mean by that: closed, we start and end somewhere. Open means it goes maybe in both directions forever. You could also just go in one direction forever. So like if I wanted to, I could have a graph that does something like this. I don't know, like that, where on the left side it stops, but on the right side goes forever. Doesn't matter, as long as it's not completely closed off, then we call it an open interval. Now, if we can do this, if we can find a way to find the highest and lowest values on a function, then the consequences of that are that we can take any function in the real world and figure out, where, let's say, if we have remember we were doing that, the two buildings connected by a fiber optic cable. If we could find that highest and lowest point, right, then we can do something with that. That would give us, like, how we build it so that we have the minimum cost, we have the lowest cost we can get. So that's the ultimate goal, is to be able to do those two things. Today, for the rest of class, is about this method. All right, that's what we're gonna do. So I'm gonna go through the notes pretty quick here because you have access to these notes. There's a lot of definitions. Don't be worried about trying to copy everything down because you can get to it. So here we go. Maximum minimum values is the name of this section. First, we have to define some things. So if you're given a curve F defined on some domain D and some number C in that domain, then f of C is called the absolute maximum value of the function on D if f of C is greater than or equal to f of x for all x in D. Okay, what the hell are they talking about? All they're saying here is if you have a function that's defined on some domain, okay, so let's say the domain here, you go from A to B, then the domain D is all the values between A and B. So you have some graph here. Here's the domain. To say that you have found a maximum value means that if you go to some value C, go up there to that point on the graph, then the value of the function at C must be greater than or equal to f of x for all the other x that are in D. In other words, this point is the highest point out of all points within that domain. So it's king of the mountain, right? Highest point on the graph. That's what it means to say you have an absolute maximum. Sometimes instead of the word absolute, we might use the word global. Okay, global maximum. Because it is, in fact, the highest point out of everything. Now, similarly, you can have this idea of a minimum, right? An absolute minimum, which would be the lowest point on the graph within the domain. Do I need to draw that, or y'all okay? You understand it would just be the bottom point. That's all right. So an absolute maximum or global maximum is the highest point of the graph within some interval. The absolute minimum or global minimum is the lowest point on the graph within some interval. Now, in either case, whether or not we're talking about a maximum or minimum, in either case, those are both called extreme values of the function. Because you can have one extreme would be a max, the other extreme is the min. The minimum and the maximum, those both are extreme values. Questions on that language? Is it pretty intuitive? Pretty clear? All right, so what's the difference between an absolute maximum, absolute minimum, and what's called a local maximum? This is tricky.
Can I
Go
take a
ahead.
guess? I'm gonna assume local means you're not given an interval and you either decide on the interval yourself or there's some type of method you go about to decide the interval that you're running on a function.
Not quite. Local has to do with the fact, let me draw you a picture first. And I think once I draw it, it'll become clear. Okay, so if I, let's say, put a graph here. Define it on an interval. Okay, so here it is, starts at A. So I have a domain here, right? Then the black point here is the G max, right? That's your global max, agreed? This point right here appears to be the global minimum, right? But what about this point in blue? What about that point right there? That's not the global max, right? But it's a local maximum, meaning it's not the king of all mountains, right? But it is the king of that mountain. So locally, it's a maximum. Now, you could also make that argument. I'm going to put L max for that. You could also make that argument for the global max itself. The global max could be referred to as a local maximum also, because yes, it is the king of all mountains, but it is also the king of that mountain. So that is also a local max. Similarly, we have a local minimum here because it's the lowest point locally. And then the global minimum is also a local minimum. So this, what makes locals weird is the fact that when you talk about king of that mountain, you're talking about like, when you're looking at that one right there, that point is the local maximum. It's the king of that little mountain. So you have to be looking only just in a little neighborhood, which is why in the definition we say near. And we've talked about this in this class already, that near is tricky when it comes to math, because, you know, what does near mean? And so this is not the precise definition that mathematicians use, but in this class, it's, you know, this should be like, huh, near, but we resolve that in a pure math class. If you're a math major, we make it very clear what we mean by near, okay? But for here, we're just gonna be like near, just kind of close and not get into it anymore. Understand the difference between a local maximum and a global maximum. Local minimum, global minimum. No questions? Okay, we move on. This very important thing. If a function is defined on a closed interval. Okay, so if your function goes here, the endpoints are always local maximums or minimums. Always. So this endpoint right here would be considered a local minimum because it is the lowest in its little neighborhood. Even though there's nothing to the left, compared to the points to the right of it, it's the lowest point in this little region. And then this point over here would be a local max. Guess what I'm saying is you don't have to have the hilltop or the valley if we're talking about the endpoints. If we're talking about the endpoints, all you have to have is one side. Just look at it from one side. Does that make sense? Any question? Go ahead, Cody. No?
Wow. I thought I had seen a different connection, but not really. I was thinking maybe there were some similar limits where you're not really concerned about at that point much as what it's doing or near the point. But I don't know that's quite right.
Kind of, because you're only caring about whether or not the points near that point are below it or above it. So like this is a local max because all the points next to it are below it, right? This is a local minimum because all the points next to it are above it. So you can kind of look at it. It's not a limit, so to speak, but it is kind of like a limit. We're looking from one side. Now I have an interesting one here for you. I'm gonna have to draw this kind of in detail here. So what if this is 1, and this is 2, and here comes the graph. Ready? I'm gonna graph the function. That's supposed to be a straight line, okay? That's supposed to be a straight line. That's not good enough. See if this one's any better.
So
There we go. So does this graph have any local maximums or global maximums or global minimums or local minimums?
it's supposed to have something because the endpoints, it's on a closed interval, so the endpoints are supposed to be something, but
Yeah. So I want you to see something here. This is kind of confusing. When we said this, look at this very first one right here. When we were talking about absolute max or global max, we said that it had to be greater than or equal to all points around it, right? Greater than or equal to. Same with the locals, greater than or equal to. So this example is weird because if you look at this, what is the value of this function all the time? This
2.
is the function f of x equals what?
2.
2. So here's what I could tell you. 2 is the global maximum of this function. 2 is also the global minimum of this function. And I could also tell you that at every point in here, pick any point you want, pick it 1, go up here. I can tell you at that point, you are looking at a local maximum and a local minimum. Because if you go to the left or right of that, it's greater than or equal to every point around it. Or you could look at it as a minimum using the same argument. So a constant function is a very unique situation because every point on the graph is a local maximum and minimum simultaneously. So, but we're not concerned about constant functions are boring, all right? There's nothing going on, okay? But it's just to kind of illustrate that we have to be careful with the language we're using here, and the inequalities actually matter. The fact that we have that bar underneath means that f of 2 is simultaneously a max and a min. It's weird. Okay, these are just examples. This is just visually to show you, here we have a graph. Here are local extremes, local min, local max, local min. Global min, global max, right? Oh, and you know what I forgot to put here? The endpoints are locals. What would this one be? A local what? This left endpoint?
Be a local max,
Local max, because it's the highest point around it. How about this one?
also be a local max.
Local max. Okay, what about this one? Now this one's a little confusing because I didn't put this here. These are supposed to be arrows going up here. So when you look at this function, it's not on a closed interval. Y'all see that? So locally, here's what we have. Local minimum, local maximum, local minimum, right? How about global? Does this have a global minimum?
Yes, it's got a global minimum right there, yeah.
Right here. This is the lowest point on the whole graph. Does it have a global maximum?
I can no, because infinity is not a real value.
No,
It's an
it just
idea.
keeps going up. So you cannot say there's a highest value here. So this would have a global global minimum of at -5. The value would be -4,975. That's the lowest point on the graph. But there is no global max because there is no highest point on the graph because the arrows imply that it just keeps getting bigger and bigger. Okay. This one, let's look at the locals. Local, 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 and the endpoints are locals. Okay. Now global. If we look at global, we have two global maxes. Well, I should say it this way. The global max is the same. The global max is 225. That's the Y value coming out of the function. It happens at two different places, right? So the global maximum is 225. It occurs at x equals 5 and at x equals -5. We also have two places where we have a global minimum. These do green dots, -64, -64, and it happens at two different places. So now we get to the theorems. First theorem, this is a very important theorem. The extreme value theorem. If f is continuous, what does it mean to be continuous? Like in layman's terms?
It doesn't stop, it's just one simple line, or continuous line, but
You can
it
draw
has a
without
limit.
picking up your pencil.
There's no pauses.
You can draw it without picking up your pencil. That's the layman's meaning of continuous. So let's say you have a function that you can draw without picking up your pencil, and you're defined on a closed interval, okay? Meaning that you're gonna start at one point, you're gonna draw, and then end at another point, and you can't pick your pencil up, okay? Let's say we start with that. Then, if that's the case, that function f must attain both an absolute max and an absolute minimum value somewhere in the interval. So start at a point, draw without picking up your pencil, stop. I guarantee you have an absolute max and an absolute minimum, guaranteed. There's no way to not have it. Here are some examples. So I don't know how easy this is to see. Let me try. I have 2 points here. I just picked these points kind of randomly here. What I'm going to do is I'm going to have the computer draw a curve connecting these 2 points. And I'm going to draw it where I can't pick up my pencil. So some random curve, here it is. Goes up, and I don't know if y'all can tell, it kind of goes up and back down a little bit. If I draw this, guaranteed, I have global extremes. I have a global max right there, and a global minimum is my left endpoint. And the theorem says that as long as I connect those with a continuous curve, I'm guaranteed to have a max and a min. There's no way to not have it. I'll give you a different example. There. Connect them with a continuous curve. I guarantee you I will have a global minimum and a global maximum here. Do another one. Straight line. Global minimum is the left, global maximum is the right endpoint. What about this one? I'm going to draw it. I'm going to put in here a vertical asymptote, and then I'm going to connect it together with the line that goes like that. Does this have a global minimum?
No,
No, since it's not continuous.
yeah, it's not continuous.
You could, yes, you could argue though that that's the lowest point on the graph, couldn't you? That looks like a global minimum, but there is no global maximum. And the reason why, and you already said this, is because this isn't continuous. So as soon as this had a break in the graph, the theorem's out the door. We're not guaranteed anything at all. So that's just an illustration of how important the continuity is. There's no way, no matter how hard you try, there's no way to take 2 random dots, connect them with the curve without picking up your pencil, and not get a global max or min. You're going to have one. I don't care what you do. You're going to have a highest and lowest point no matter what. All right, I'm going to skip Fermat's theorem because it confuses people. There's a second version of it that's better. Okay, so I need to define something for you. Let me do it this way. Before I get to this, I want to show you a couple of pictures, a couple of graphs. So let's say I had a graph that was pretty simple, something like that. Do you all agree that these local maximums here, the local max here and local min here, that if you were to take the slope of the tangent line, you would tell me that at those points the derivative is 0. Here and here, whatever it is, the derivative is 0. Do y'all agree? So it looks like local maxes and mins seem to appear whenever the derivative is 0. But that's not the only thing that could happen. Here's another picture. Is that continuous? That picture, is it continuous? Yes. Okay. Do you see that at each of these points, here, 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 we have local extremes, local max, local min, local max, local min, local max. What can you all tell me about the derivatives there?
They're undefined.
They're undefined. Very good. Because Justin said undefined, because remember when we talked about derivatives, we said if we have a corner, right? A corner or a cusp, then the derivative doesn't exist. So at these points, the derivative isn't 0. The derivative does not exist. The derivative does not exist here. 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 At all of those corner points.
Did you say or a cusp?
A cusp would look like this.
Oh, okay. Understood.
Yep, these are all considered cusps. The difference between the cusp there and the corners, that corners come together like with straight lines, where cusps have curve to them when they come together. So
That makes sense.
same thing though, for each of these cusps, the derivative doesn't exist. So now I have a question for you, just think about this. I'm going to move this. I'm going to go to a different page because I want you to think about this here. All right. So is it possible? Well, how do I want to say this? Let me write it down first, see if you agree with this. If, so agree, yes or no? Agree, yes or no? If some function is continuous and has a point C where the derivative at that point is 0, or the derivative at that point doesn't exist, then we must have a local max or minimum there. I want you to read that and think about it and agree yes or no that this is true. So I'm saying if you have a continuous function that you can draw without picking up your pencil, and then at some point in that interval or some point in that domain, I tell you that the derivative is 0, or I tell you that the derivative doesn't exist, then can you conclude from that that at that point we must have a max or a min local? So think about it. Let's do a vote. Does anyone need me to clarify the question? Here's the poll. So is this true, yes or no? If you're looking at a function and you find some place where the derivative is 0 or doesn't exist, then that means you're looking at a point where you either have a local max or min. Anyone need clarification? I think that's almost everyone. So the results of the poll there, 79% of you think that this is true, and then 21% think it's not. So let me start with the people, because only 3 people thought that this wouldn't be true. So does someone who said that they don't think this is true want to kind of explain their reasoning here?
Well, the reason why I said no is because doesn't the extreme value theorem say that that it's guaranteed to have a global max and min only? It doesn't guarantee you the locals, right?
Yeah, that's true. That's true. It doesn't guarantee you the locals. But if you're on a closed interval, the endpoints would have to be locals, right? So you're gonna have to have locals no matter what if it's a closed interval. What I wrote here we're not even looking at a closed interval though. I never said in here it had to be closed, right? I'm just trying to say, if you look at a function, you find a place where the derivative is 0 or doesn't exist, does that guarantee you that you're looking at a local max or min? So let's see, someone else who said no, have a reason? Or want to get into the reasoning? So, okay, let me guide us through this then. Let me draw a curve, okay? Let's start out with something very simple. Right there. At this point C, what is the derivative here? What's the derivative at C?
0.
0, because the slope of the tangent line is 0. So we have a point C where the derivative is 0, and obviously this is a local maximum, yes?
Yes.
Is it possible to have that happen, to have a derivative of 0 at some point, but it not be a local maximum? How about that? So look what's happening right about here. What would the slope of the tangent line here be?
0.
0. And is it a local maximum? Is this a local maximum or minimum?
No,
No.
it depends on what direction you come from. If you go from the right, it'd be min, but from the left, it's max, so it's neither.
It's, yeah, it's not a lowest point, it's not a highest point. So what am I saying to you? I'm trying to get you to see, just because the derivative of a function at a point is 0 does not guarantee you that you're looking at a local maximum or minimum. Unfortunately, that's not enough. Okay, it's not enough. To say that the derivative is 0 somewhere does not mean that you're at the top of a hill or bottom of a valley. It's just not quite enough, because there are examples where this doesn't work. Let me show you another example. How about this? Okay, if we go to C here, up to this point, the derivative at that point does not exist. And that's a local max, right? It's a local max. But is it possible for me to draw something where I would have at some point C a derivative not exist and not have a local max or min? And the answer is yes, I can do it. Here it is. That's a little too extreme. Let me go. There we go, like that. So at C here, if you go up to where the point is and you look at the slope of the tangent line, well, wait a minute. That slope of the tangent line is vertical, isn't it? And what's the slope of a vertical line?
Undefined.
Undefined. So the derivative at that point C does not exist. But look, that is a continuous function, right? I drew it without picking up my pencil. And the derivative doesn't exist there, but it is not a local max or a local min. So I hope what you're seeing here is the two drawings on the left are kind of like what you would think is true, but the two on the right are just show you counter examples of why we cannot say that this is always true. Okay, so this is not always true. Now here's what we can say. Now I'm ready to give you the theorem. Oh no, I need one more thing before I do. So we're going to define something right now called a critical number. Okay, this is a very simple idea. Don't make it more complicated than it has to be. A critical number of a function is just some number C where the derivative is either 0 or the derivative doesn't exist. So if you're looking at a function, all the places where the derivative is 0 and all the places where the derivative doesn't exist are called critical numbers of the function. Critical numbers. So if we look at that picture I just drew a second ago, this value C is a critical number because the derivative there is 0. Here at C, the value here, this value C is a critical number because the derivative here doesn't exist. But this is also a critical number because the derivative is 0. And this right here is a critical number because the derivative doesn't exist. So anywhere where the derivative is 0 or anywhere where the derivative doesn't exist, you're talking about a critical number. Now, why are critical numbers important? Because of the next theorem, Fermat's theorem. if your function has a local max or min, if it does, okay, it may not, but if it does have a local max or min at some point C, then I guarantee you that that must be a critical number. Okay, we have to, this has to do with logic, okay? What we're saying here is that if your function has a local max or min, then I promise you that you either have a zero derivative or an undefined derivative. It does not say that if you have a zero derivative or an undefined derivative that you have to have a max or min. It's the other way around. This will all come to light, I hope, when we start doing examples. All right, if all of that is just confusing you, all that really matters at the end of the day is that you know how to find the absolute max and mins of a function on a closed interval. And that's what I had started with. I said today, second half of class, our goal is to be able to find the highest and lowest points of a function on a closed interval. And the good news is that there's just a few steps that you have to do. Okay, this is it. These are the steps. To find the absolute maximum and minimum values of a continuous function on a closed interval AB, here's what we do. First, we find the critical numbers. What are critical numbers? Anywhere that the derivative is zero, anywhere that the derivative is undefined. We find those values, where they occur. Then we evaluate the function at those critical numbers. We also evaluate the function at the two endpoints. And then we compare all of our answers and just pick which one was the biggest and which was the smallest. So let's do an example. I'll refer back to as well, you know, I'll copy it so we can use it. All right, so here we go. I'm going to give you a function. I'm going to give you a closed interval, and I'm going to ask you to give me the highest and lowest values of this function on the interval. So here's a function. F of x equals x cubed minus 4x squared. And I want you to look on the interval -1, 3. I need to give you the instructions. Find the absolute max and minimum values. I could have asked you to find the global extremes. That's another way I could have asked you to do this. Find the absolute maximum and minimum values of this function, or I could have said, find the global extremes. So I look at this thing. First thing I do is look at the function, and I say it's continuous. Why is it continuous?
The cube and the x squared.
Yeah, it's a polynomial, right? All polynomials are continuous. So it's continuous. Then I look at this. That's a closed interval. To find the global extremes of a continuous function on a closed interval requires the closed interval method. And that's the 3 steps that you see in front of you. Okay? So first step, I need the critical numbers. Which means I want to know where this function f, where its derivative is 0, and I would also like to know where its derivative does not exist. Those are the 2 things I need to figure out, because that's what it means to find the critical numbers. So if we're going to try and figure out where the derivative is 0, and where it doesn't exist, then we're going to need the derivative, right? So we may as well take the derivative right now. So the derivative of this function shouldn't require much of your brain. Right, there we go. 3x squared minus 8x. That's my derivative. Now, I'm going to set it equal to 0 first. Take your derivative, set it to 0. So I'm going to try and figure out where this thing equals 0. See, this is what it means to find the critical number. Figure out where the derivative is 0, figure out where the derivative doesn't exist. Take the derivative, set it equal to 0 first. That is quadratic, but I can factor the left-hand side. I can pull an x out. I get 3x minus 8. And then I can set each of those factors equal to 0. And I get two solutions, 0, and the other solution is x equals 8/3. Or 2.666, something like that, right? It might be worth it for us to know that this is about 2.66 repeated. The reason why I'm interested in knowing about these numbers, because I need to make sure that these critical numbers are in our domain. So do both of these numbers appear in here?
Yeah.
Yes, okay, so we want to keep them. If let's say one of our answers was like 4, okay, let's say it was x equals 4, I wouldn't even use it. I would throw it away because we're only looking between -1 and 3. All right, that's the first part. I had to find where the derivative is 0. Now, I also have to figure out where the derivative doesn't exist, right? Where does it not exist? Well, my derivative is 3x squared minus 8x. And if you look at that derivative, there's nowhere it doesn't exist. There's no square root, so I don't have to worry about square roots of negative numbers. There's no fractions. There's no division by 0. It's a polynomial. It's a very well-behaved function. There's no issues here, right? There's no issues with the derivative being undefined. Which means I only have two critical numbers, 0 and 8/3. So now what I do is I take those two answers and I plug them into the original function. I take the original function f and I plug in 0. I take 8/3 and I plug it into the original function. So let's see, the original function was up here, x cubed minus 4x squared. So it'll be easy to plug in 0 because I just get 0. 8/3 might take some work. 8/3 cubed minus 4 times 8/3 squared. I may need my calculator for this. I will need my calculator. Anyone have any questions while I'm doing this?
So basically just to find the critical numbers, we're just gonna set equal to 0 and basically just find our x-intercepts almost.
Yeah, you could look at this as we're solving for the x-intercepts of the derivative.
Right, of the derivative.
Uh-huh. Okay, so 8 divided by 3. I'm getting here approximately -9.48, something like that. Is what I get when I plug in 8/3 into the original function. Go with me? That's step 1. Find the critical numbers and evaluate the original function f at those critical numbers. Done. Got it. 0 and -9.48. Now step 2. Endpoints. What I want to do is I want to evaluate the original function at the two endpoints of the interval. The two endpoints were -1 and 3. So now I'm going to plug in f of -1 and f of 3, and that's going to go into the original function, right? Be careful there, not plug it into the original function. You should get -5, and then I get -9. The last step is to compare the answers from parts 1 and 2. The largest is the absolute maximum, and the smallest is the absolute minimum. So for step 3, let's talk about the absolute maximum first. So what is the largest out of the numbers that we just found? It is this,
0.
this, and this.
0 is the
0, right, is
largest.
the biggest number that we have.
Mhm.
So the absolute max is 0, right?
Yep.
Now, I like to do this. I actually like to write it as a point. Because what did we get to get 0? We had the x value had to be 0, right? So it's actually the point 0, 0. The absolute value, I'm sorry, the absolute maximum value is 0, but to write it as a point helps you see where it happens. You'll see on the next part. Absolute minimum. So what's the absolute minimum of this function?
The approximately negative 9.48.
Negative 9.48 is the absolute minimum. Now, written as a point, where does that happen?
Be 8/3 and then comma negative 9.48.
Negative 9.48 approximately. So I'm going to write 8/3 as the decimal because I'm going to write this as a decimal anyway.
Okay.
But you could do 8/3, it's fine. And that's it, we're done. So what we're saying, I mean, just kind of take a step back. What we've determined is if you were to give me this function and just tell me to look between -1 and 3, we have found where it has its highest and lowest values, where it happens and what they are. And you can confirm this with a graph. If I go to x cubed minus 4x squared, and I just look between -1 less than or equal to x less than or equal to 3. So there's the graph of that function between -1 and 3. There's the graph. We found the point 0, 0. And we found the point 8/3 negative 9.48. Was that what it was? Something like that.
Mhm.
And look at them. Can you see it? There it is. That is the local maximum. I'm sorry, the global maximum right there. 0, 0, and the global minimum of 8/3 or 2.66, negative 9.48. That works for any function on any closed interval, as long as it's a continuous function. So we now have a method in our toolbox to find the biggest and lowest values of a function as long as it's continuous and on a closed interval. And it's not that bad. You have to be able to set the derivative equal to 0 and figure out where it's undefined. Let's do another one. How about, I'm going to copy this so I don't have to write it down again. Square root of x plus x on the interval 0, 9. All right, what's the first step? Let me see, let's call someone. Roger, are you here? No, there's no Roger. How about Gabriella?
Yes, sir.
Okay, you ready? Step 1, critical numbers, right?
Yes, sir.
How do you do that then?
Find the derivative of f of x.
Okay, can you give me that? What is the
Uh,
derivative of this
1
function?
over 2 square root x plus 1.
Plus 1. There we go. That's it. Good. Now, what do you do with that, Gabriella?
Don't we plug in 0 to find the x's?
We have to set it equal to 0.
It's
We have to first set the derivative equal to 0, which means we have to take that answer and set it equal to 0, right?
Yes, sir.
Everyone with me, with us? Okay, now at this point, Gabriella, we have to solve this equation. Now look, do you remember I was saying to you in the beginning, raw derivative, but eventually you're gonna have to do algebra? Like we've now reached that point where we have to solve equations. So now it's gonna pull from your college algebra experience, how good are you at solving equations? We've kind of navigated our way through calculus without having to do too much heavy duty solving of equations, but the time has come, all right?
Yes, sir.
So, Gabriella, I mean, I hate to put you on the spot here, but you know, any idea of how you would go about solving this?
Because we're just trying to get to where it's just x, right?
Yeah, we just want to know what x makes this true, right? Is what we want to know.
Yes, sir. So I'm sorry. What do we move
Okay.
-1 to the other side?
You want to do the 1 to the other side?
That way.
Fine, I'm okay with that.
Okay. And then multiply both sides by 2 square root x.
This is all legal algebra, okay? Gabriella is doing just algebra. I think you're clearing fractions right now. You're getting 1 equals -2 root x. Okay.
And then divided by -2 on both sides.
Good,
And-
that's all legitimate algebra. Good,
Square both sides.
square both sides,
Yes, sir.
okay? Okay, the left side is -1/2 times -1/2, that's 1/4
Mhm.
equals,
X.
so x is a fourth? Is that what you're getting?
Yes, sir.
Y'all follow that? Okay. Should I move on? Anybody have any issues with this? Gabriella, that was excellent. Okay,
Thank you.
very good. I'm encouraged by that, but it's wrong. Now, it's only wrong because you did something that was legal. Everything you've done is legal,
Okay.
except one thing. When you
Plus or
square both sides, go ahead, Gabriella.
It's a plus or minus because you took out the square root.
No, when you square both sides of an equation, right? This goes for everyone. When you square both sides of an equation, you introduce the possibility of extraneous solutions, meaning you could get an answer that doesn't work. And so you have to check your answer. If you ever square both sides of an equation, you must check your answer. And we're going to check this answer and we're going to see it's not right. Because if you take 1/4 in and just, I don't know, plug it in anywhere before you square it, right there, plug 1/4 in here. You'll get -1/2 equals the square root of 1/4. And that's -1/2 equals the square root of 1/4 is a half. And these aren't equal. Another way you could have seen this, look, is if you go, let me go back up to this step right here before we did anything. 1/2 root x equals -1. Think about this for a second. Your answer needs to be -1. The numerator is 1, right? That's positive.
Mhm.
2 is positive. When you take the square root of a number, can you ever get negative?
The square root of a number, no.
No, right? I mean, there's no way. Give me the square root of any number. I don't care what number it is. As long as it's not imaginary, okay? You're not allowed to use the I here. You know, give me any number. If I take the square root, my answer's got to be positive, okay? It's got to be positive. So if I have a positive up top and a positive here, and I know that the square root of any number is positive, it will be impossible for me to get a -1. So at this point right here, we could have just said no solution. Now we did the algebra, and Gabriella, all that algebra was perfect, except the part of checking. And you only have to check it if you square both sides, if you do that, right? If you do it, then you have to check it. And so when we check it, it doesn't work, and therefore we have no solutions to that equation, which is okay. It just means we don't have a critical number for this part, right? The derivative being 0. I don't know how far down the rabbit hole we want to go here.
Can
Does
you hear me or
anybody-
am I lagging?
What's that?
Oh, I guess I was lagging. I was gonna ask, so does this go for any time you put a positive exponent? So if I were to put the, -1/2 to the 4th and then square root of x to the 4th, would I also have to check because it's,
If you raise both sides of an equation to an even power, you must check your solutions. If you
Okay.
go to an odd power, it's okay. You don't have to check. I mean, you should always check just to check, but you can, when you square or raise to the 4th or 6th or 8th, you always have the possibility of extraneous solutions, not guaranteed. You may have correct answers in there, but you may also have ones that are wrong.
okay.
So the rabbit hole I didn't know if I wanted to go down was this right here. When I had written this down, how many of you were thinking that this should be plus or minus? Don't answer that question. Here's the deal. The only time you get a plus or minus on a square root is when you take the square root on both sides of the equation. Okay, so if the square root was just there, then it's just the positive root, which we call the principal root. It only has the plus or minus if you initiated the square root yourself. So like, for example, if I write x equals 4, or let's say x squared equals 4, and I want to get x, if I do square root on this side, and I do the square root on the other side, then I have to look at both the positive and negative cases. And this would be x is equal to plus or minus 2, okay? But if somebody else were to write this down, x equals the square root of 4, okay? If that was just written down, your answer is 2. That's it. There's no plus or minus because the square root was there already. You did not create the square root. All right, I know that's confusing. That's why I don't want to go too far down that rabbit hole. All right, we're only halfway. Gabriella, great job on the algebra there. Really good. Marissa, I think Marissa's next. Is Marissa here?
Yes.
Okay, Marissa. How are you doing? Is your audio any better? Think we'll
It's
be
okay. My connection is just really, really bad.
Okay, let's see how this goes. Gabriella had us getting the critical numbers. The first thing we do is figure out where the derivative is 0. Now we need to figure out where the derivative is what?
Where it equals, we're finding the endpoints right now, aren't we? Or no?
Nope, we're finding the critical numbers. The critical numbers are where the critical numbers of a function is a number C in the domain such that either the derivative is 0 or the derivative doesn't exist. Gabriella got us through this part. Now we need to check this part. Then we'll get to the endpoints, okay?
Okay.
So we still need to check here, where does the derivative not exist? So Gabriella, I'm going to write down the derivative. And I want you to look at this derivative and tell me just by looking at it, are there any values of x that you can't plug in or else you'll have a problem?
Negative numbers, anything.
Oh wait, did I say Gabriella or Marissa? I'm sorry.
Gabriella.
I'm sorry,
Yeah,
Gabriella.
I say Gabriella.
Sorry, I meant
But
to
I
say Marissa.
agree with what she said.
I didn't hear what she said. The audio was weird. I didn't hear it.
So you,
Oh, she said anything negative.
Okay, anything negative, I agree. Do y'all agree with that? Anything negative won't work, but wait a minute, Marissa, look, up here, 0 to 9, we're not even looking at negatives. So we don't need to worry about that. So Marissa, is there anything else other than negatives that would cause a problem here?
0.
Mm.
Cody, you're not
Oh.
Marissa.
Sorry, I thought my mic was muted. My dogs keep stepping on my big Sam. I'm serious. I was trying to answer before you said it and it's all a miss. Oh
It's
my
okay.
goodness.
It's okay. All right, so Cody said 0, Marissa. Do you agree with that?
Yes.
So the square root of 0 is 0, right? And then we'd have division by 0. And 0 is in here, isn't it?
Yeah.
Okay. In fact, you can plug 0 into the original function, can't you? You're not going to get division by 0 here. You can plug 0 in here and 0 in here, there's no problems, but there is a problem with the derivative. So we would have to say here, x equals 0 is a critical number. All right, so again, finding critical numbers, take the derivative, set it equal to 0, solve, hope your algebra is good. Second part of that, take the derivative, figure out where it doesn't exist, analyze the function, look for domain issues, point out anything that causes a problem that lives in this interval. And now we're ready for the second step. The second step is, and this is what Marissa was saying, the endpoints, right? So that means all we're going to do is take the two endpoints, 0 and 9, and plug them into the original function, right? Oh, wait, you know what I forgot to do? I'm sorry, I got ahead of myself. In step 1, what are we supposed to do? Find the critical numbers and then evaluate the function at those critical numbers. I forgot to evaluate the function. How many critical numbers do we have?
Just one.
Just one, right? The only critical number we have is this one right here. So we just need to check out and see what the function's doing there. So the function at 0 is the square root of 0 plus 0, which is just 0. So as a point, it's the point 0, 0. Now we can move on to the next step, which is the endpoints. Got to go to the next page, sorry. And if we plug in 0, we just plugged in 0, didn't we?
Right, it's 0, 0.
0, 0, okay, we know that. But what about 9?
Be
Square root
9,
of 9
12,
plus
right?
9 should get 12. So as a point, this is the point 9, 12. So after all this work, right, the absolute max, well, we only had two things to compare, right? At 0 and 9, the two endpoints, that was all we had. Well, I mean, we had the other critical number, but that was 0. That was the same as the endpoint, wasn't it? So really, we only had two things to compare. So the max is going to be 12. And that happens here. So this right here is our max. And this right here is our min. Or min is 0, I should say.
When we say like the min and the absolute min and the absolute max, would it be better to write it in point form? So like absolute max is 9, 12, or does it just 12?
Okay, technically the maximum value is 12.
It's a Y value.
The 9, 12 is just as a reference as to where it happens. I like to see it written as a point, but just the 12 would be correct.
Okay.
Yeah. All right, so let me see here. I'm going to graph it real quick. It was the square root of x. No, square root of x plus x. Oh, and we were looking between 0 less than or equal to x less than or equal to 9. All right, pretty boring, huh? I picked a pretty boring function there. There it is. All right, what time is it? 4. Let's do, I'm gonna give you one now. You ready? I'm gonna throw you to the wolves here. So I'm gonna show you the graph of it first, all right? Because I'm gonna kind of cheat here. I want to stay within the, I want to kind of keep you away from certain algebra here. Give me a second to. I just don't know how far I want to push you right now, so I want to see if this is consistent. Yeah, let's make that squared. There we go. Let's go for, yeah, okay. So there's the graph. We're gonna go f of x equals x times the square root of 16 minus x squared on the interval 0 to 4. Find the absolute maximum minimum values. Do y'all want the steps up here or no? Well, I guess it won't hurt, huh? All right, so there you go. Let me give you about 10 or so minutes and just see how it goes. I promise you, the algebra is going to be the thing that gets you now. But you have to get the derivative right first, right? You get the derivative wrong, then everything else can be wrong. So see how it goes, all right? I'm sure we'll have questions. We'll talk in just another minute. I put the derivative up here just to make sure you at least got through that part. Okay, let's talk. What are y'all thinking?
I got the derivative, but for some reason I'm just struggling on figuring out what I need, like how I need to set it to 0.
Okay, yeah, that's where most people are going to have issues. Because we've focused a lot just on getting the raw derivative, right?
Right.
So does anyone have a question on the derivative itself? Product rule. Here we got product f and g. So I do f prime g plus g prime f. The g prime requires chain rule. So derivative of the square root of something is 1/2 square roots of that something. Derivative of the inside is -2x. This x is from the product rule, the f. This part's pretty clean, I think. And then I just did cancel the 2's. X times x is x squared. Move the negative out here. So we're good on the derivative. Setting it equal to 0. That's where things become problematic. So the rule of thumb here, oh, I forgot to put equal 0 there. The thing I like to do whenever I have equations like this, where I have multiple terms and I have fractions, is to get a common denominator. So I look at this first fraction as this over 1. And I try and put these together with a common denominator, which means that I would have to introduce the square root of 16 minus x squared on the bottom, square root of 16 minus x squared on the top of this fraction. And when I multiply these two together, the square root goes away. So I'm left with 16 minus x squared. That's going to be on top of this square root. And then I'm going to subtract from that this numerator, right, over the same square root. So that should be all of it over the square root. That makes sense?
Mhm.
Now, do you remember what I told you about fractions being 0? Fraction can only be 0 when?
When the top is equal to 0.
When the top is 0. Good. Do y'all remember me saying that? I know I've said this because I knew we were headed here. All we have to look at is when this top is 0. So the top is actually 16 minus 2x squared. I want to know when that's 0. And now I'm just going to move things around. 16 equals 2x squared. Divide both sides by 2. I'm going to take the square root.
So plus or minus.
Plus or minus root 8 equals x. So I have two answers here, root 8 and negative root 8. And I'm going to throw away the negative root 8. Why?
This is a negative and you were dealing with real numbers, and that'd be an I or imaginary.
No, because the negative is outside the root, not under the root.
The
It's
interval
below
one.
the interval.
The interval we're looking is
All
between
right.
0 and 4.
Right, right.
Had this been like -4 to 4, I would have kept it. But because it's 0 to 4, I'm only looking at numbers between 0 and 4, so negatives I throw away. And the square root of 8, if you need to check that on your calculator to make sure it's in the interval. It's about 2.83. This is approximately 2.83. So that's definitely in the interval. So we have one critical number so far. One critical number. Something interesting is happening at the square root of 8. Now, I also need to figure out where the derivative doesn't exist, right? So this is tricky also because you're looking at this nasty derivative and you're asking yourself, what values of x are going to mess this up, right? Well, look at the original function. The original function has a square root of 16 minus x squared, right?
Mm-hmm.
And every value between 0 and 4, if you plug in 0, you get 16. If you plug in 4, you get 0, right?
Mm-hmm.
So any number between 0 and 4 should be okay to put in here. We have no issues plugging numbers between 0 and 4 into this. But when you get to here, look at this is in the denominator.
Can't have
So
a 0
if
or
I
negative.
if I plugged in what?
If you plugged in anything greater than 0 or anything less than 0 or greater than, well, no, 4 or 0 would give it to you.
Well, we have to stay within this interval. So I'm saying, are there any points between 0 and 4, including 0 and 4, that would cause this to be a problem? Do y'all see at 4 we have a problem?
4, yeah.
Right, yeah. Well, 0
And
too.
0 in
there's-
the denominator.
Well, no, not 0
0
would be
is okay
fine.
to have.
Yeah, yeah.
0 is okay to have because 0 here would give you just square root of 16. That's okay. But we get division by 0 if we try and plug in 4. So we have two critical numbers. So what I'm going to do now is I'm going to take the original function and evaluate it at those two critical numbers. I'm still in step 1. So I go to the original function, I replace my x's with the square root of 8. So I get square root of 8 times the square root of 16 minus the square root of 8 squared. And when I square the square root of 8, I get 8. This becomes root 8 times root of 8 again, right? Because square root of 8 squared is 8, and 16 minus 8 is 8.
Right.
So I'm getting root 8 times root 8, yeah?
Which is 8.
Which is just 8. And then we have to plug in 4. So if we plug 4 into this, we're going to get 4 times the square root of 16 minus 4 squared. But 4 squared is 16, so 16 minus 16 is 0. This whole thing should be 0. Now we move on to the next step, which is to check it at the endpoints. So I need f of 0 and f of the other endpoint, which is 4. These are the endpoints. All right, now f of 0 should just be 0. If you plug 0 into the original function, you get 0 in the beginning, everything else goes away. And we just saw that when we plugged in 4, we already know what happens. We get 0. So for the final step 3, our absolute max, what is the maximum value of this function?
8.
8. Now written as a point, it's root 8, 8. And then the absolute minimum of this function is what? What's the smallest value we see?
0.
0, but it occurs where? When we plug 0 in, we get 0, and, right? And when we plug in 4, we get 0. let's go back and take a look at the graph. Here was the graph, but I only wanted to look at it between 0 and 4. So if you look at this graph between 0 and 4, we found an absolute maximum at the point square root of 8, 8, minimums at 0, 0, and 4, 0. So I hope you can see that our max, that red point is root 8, 8, and the minimums are here at 0 and 4. Now, I know that you're probably sitting there going, well, you know, why go through all that trouble, right? Why go through all the trouble when we can just look at the graph and ask, you know, the computer to find that maximum value? And that's a good question, because a computer can do this pretty easily, find that highest and lowest values. So this is kind of, you know, what we're trying to do is make sure that you can do it mechanically by hand, but in the real world, you use computers. Once you have the function, you use a computer to find the max and mins. But this goes back to a conversation we had before, like, you can't stop teaching the theory. You still have to have the theory because people have to program the computers to do the theory. So, you know, this is a math class, we learn the theory. All right. Let's see, I'll give you another one here. This will be our last one for the day. What time do we end? 4:20, 4:30?
4:30, we've got 9 minutes.
And I don't know if that's enough time.
You want to give us one to work on and have
Yeah,
bring
why
something
don't I-
for next
yeah,
class?
why don't I give you another quiz problem? Just a one problem, one question problem. Let me just real quick.
Tuesday of next week.
We'll keep it pretty nice. Okay, so same thing, find the absolute max and minimum values. Give me a moment, I'm just gonna go, I'm gonna graph it, but I'm not gonna show that to you. So I just wanna make sure it's gonna work out the way I want it to. Almost done, hold on. There we go. 1, 3, 1, 3, 1, 3. Okay, here's the function. X over x squared minus 4x plus 2. So I want you to find the absolute maximum and minimum values of that function on the interval 1, 3. I'll send you a Dropbox link. This will be due start of class Wednesday. So 6.
We don't have class on Wednesday, sir.
Oh wait, not Wednesday, Thursday. I'm sorry. 6/8/21. I'll send you a Dropbox link. Okay, now in terms of homework for our schedule here, of course, you've got all that L'Hopital to do, okay? But for max and min, I would say just to focus your attention on I'm going to change the assignment a little bit here. Max and min, don't worry about these. Worry about 23 just for now. If you look at these right here, just for homework for these, if you do these, this will maybe help you do the quiz problem. If you can do these, so maybe do those first and then go do the quiz or whatever you want to do, but at least do those for homework. And that's it. We'll be back on Wednesday. We got more to do here and then we'll move on.
And we can pop in office hours with the quiz.
Sorry?
Saying we can pop into the office hours for this quiz as well. So talk about it if
Yes.
we need to. Okay.
Yep. All right, everyone.
Ready,
Can you
sir?
hear me? I'm sorry.
Okay.
I don't know if my audio is working now.
You're good.
Good. Was that a question, Jorge?
Yeah. Sorry, I don't think my audio was working. I updated drivers and it was getting the mic from my speaker. Can we expect a review soon? I think we test next week or
Next Tuesday, the 13th.
Yeah.
Is it a week? Yeah, I should probably send that out. You'll probably, yeah, I'll get that to you by Thursday. Probably Thursday.
Thank
I
you.
mean, I probably have the review already. I just have to tweak it a little bit, but yeah, I would expect that. We still have 2 more things to do before, so we should wrap that up on Thursday.
It'll have 2.5 and 2.6 on there as well, right?
Yep.
'Cause okay.
We only got up through 2.4, so it's going to be a pretty intense test. Chain rule, implicit related rates, exponential log, L'Hopital, this stuff. So let's see how things go on Thursday, and that'll determine what will be on the test, but expect a review. All righty, everyone. Have a good day. Take care.
Thank you, you too.
Thanks.